Okay, let's continue. So what happens if you deal with a pressure that is higher than your critical pressure? So that pressure is called supercritical pressure, and here there is no a distinct phase change process, as we cannot identify when exactly does a phase change occur. So most of the time, okay, at all time, the during the when you deal with supercritical pressure, you will be at only one phase, okay, which is vapor phase. So now let's proceed. So here I have a TV diagram. So if you the saturated liquid states, okay, at different pressure. So if you relate this slide, the slide on page 18, okay, this is your different pressure line on a TV diagram. So here, the one that I circle here, the first point of your saturation line is your boiling point, or we call it saturated liquid point. So if you connect this point, okay, and the point, this point on the end of your saturation line, which is your saturated vapor point, if you connect it, and these two lines, saturated liquid line and saturated vapor line, then will meet at the dome, okay, which is the critical point. That's the dome, okay. Whatever underneath this dome, this is your saturated liquid vapor, liquid vapor mixture, okay. And whatever is outside and on your left side is the compressed liquid, and the one that is to your right side, okay, this is left and right, this is your superheated vapor region. Superheated. Okay, so this figure is more clear. So you need to know what is the three main different region, okay, and you can actually relate this with this one, page 8, okay, slide number 8, when we learn about phase change process of a pure substance. So at state 1, it is compressed liquid or subcool, okay, it is on your left side, okay. Then once your water start to boil, okay, like this point, it is the saturated liquid, and as more heat is transferred, and you will have the saturated liquid vapor mixture. This happened on your saturation line. And the last drop of liquid, when you want to vaporize that last drop of liquid at 100 degrees Celsius, state 4, that is when you reach your saturated vapor on the saturated vapor line. And if you heat up, put as more heat is transferred, you will have outside the region, okay, which is the superheated vapor. So I hope you're able to relate this slide with the slide on page 20, okay, these three regions. So I want to show where you can get the values of properties for each region. So you need to look at your appendix, okay, appendix 1. So here, table A4, okay. Table A4 and A5 is for saturated liquid vapor mixture. Table A6 is for saturated vapor, and table A7 is for compressed liquid water. Okay. Right here. So here, this is table A4 and A5, okay, depending if you at which this one they specify T, while A5 is for pressure. Compressed liquid region is table A7, and for superheated vapor region is you need to refer to table A6. Okay. From that table, you can get the value of enthalpy, your specific volume, and all the necessary information that you will use for your calculation. Right. So next, let's look at a PV diagram. So the general shape of a PV diagram for a pure substance is very much the same like a TV diagram, except that okay, the axis, y-axis is obviously different, and your T constant line here, they have a downward trend. So just now, your P line, okay, this is your P line, pressure line, the trend is upward. So from here to and go up. So for PV diagram, the temperature will go down. So downward trend. So in this case, if you reduce pressure by reducing the weight from the piston, okay, we will water is allowed to exchange water inside the piston. Okay, water is allowed to exchange heat with the surrounding, so its temperature will remain constant. So when P reach the saturation pressure value at specified T, the water will start to boil. Right, water will start to boil here, and during the vaporization process, both pressure and temperature remain constant, but the specific volume will increase. Okay. So next is the if we extend the liquid vapor diagram to include another phase, we will have a three-phase diagram. So in previous, the two equilibrium diagrams discussed so far represent the equilibrium states involving only liquid and vapor phase. However, this diagram can be easily extended to include solid. Okay? The figure here shows a PV diagram for substance that involves solid, liquid, and vapor phase. Okay, most of the substance contract during freezing. And the diagram on your left, okay, shows the PV diagram of this substance, the substance that contract during freezing. So others like water, okay, expand as they are freeze. Okay, this is for that contracts. Okay, the one on your left side is the one that contract, and this side is expand on freezing. They will have a slight angle here on freezing, such as water. So these two diagrams differs only in the solid liquid saturation region. So if you see this side, you have a slight angle, and this one is a straight line. So your triple point is here. Okay. So the fact that water expanded upon pre-freezing has a vital consequence in nature. Okay, if water contract, okay, water should expand. Okay, but if water contract on freezing as most other substances do, the ice form would be heavier than liquid water, and it will settle at the bottom of rivers, lakes, and ocean instead of floating on the top. Okay, that will be a problem for us. Okay, the sun rays would never reach this ice layer if it's at bottom. Okay, the bottom of many rivers, ocean will be covered with ice, and it will seriously disrupting marine life. So that's why in nature water expand. Water does not contract because of the reason that I explained just now. So here we have a triple line. It is a horizontal line in a PV or TV diagram for triple phase state, solid, liquid, and vapor, where all these pure substance coexist in equilibrium. The states on the triple line of a substance should have the same pressure, temperature, but different specific volume. Okay, different specific volume. Because at this line it's horizontal, like, so your specific volume will be different depending on your temperature and pressure. Okay, so this figure here shows a PT diagram of a pure substance, and this diagram is often called a phase diagram since all three phases are separated by each other. Okay, you have vapor, liquid, solid separated by each other by the three major lines. So here you have a melting line, vaporization, and sublimation line. And all these three, okay, here, this is your triple point. The sublimation line separates solid and vapor region. Okay, the vaporization line separates liquid and vapor, while your melting line or fusion separates the liquid and solid region. So it meets at the triple point where all three phases exist in equilibrium. All three phases exist in equilibrium. Okay, the vaporization line here will end at a critical point. We have covered a critical point initially. This is between liquid and vapor, because there is no distinction can be made between liquid and vapor phase above critical point. Right? And substance that expand and contract on freezing differs only in the melting line on the PT diagram. So here, I want to show you where you can get the values for triple point. So go to your textbook. It's in chapter 3. Chapter 3, table A3, not A, table 3.3. Okay, here we go. Table A3, 3. For values for temperature and pressure for these various substances. Table 3.3 textbook. Chapter 3, it's not in the appendix. For temperature triple point and pressure triple point. So, okay, let's look at this last slide here. Okay, there are two ways a substance can pass from solid to a vapor phase. No substance can exist in the liquid phase, okay, in a stable equilibrium at P pressure less than PTP. Okay, let's see what I meant here. Okay, for a substance that have a PTP, a pressure above atmospheric pressure. So if your pressure is less than pressure of TP, you will be dealing with solid and vapor, and that's go for sublimation process. That's the only way to change from solid to vapor phase. And one example sublimation process is dry ice. Okay, and for if pressure more than PTP, you will be dealing with melting and vaporization process. So basically that's what we can conclude from this slide. So with that, we finish phase diagram topic. we will continue the other topics in the next lecture.